Welcome back to module 3 of the course time dependent quantum chemistry. We have been discussing how to represent a particle in quantum mechanics, and we have seen that the wave packet is the correct representation of a particle in quantum mechanics. And in terms of wave packet, we have got an analytical approach to solve the dynamics of a wave packet, and for that, first thing we need is that the initial wave packet has to be known to find out how that known wave packet will move forward, or in other words how the particle will evolve. So, it is more like if I start with a Gaussian wave packet, then at different time it may so happen that it is moving, but at the same time is broadening when the particle is moving, which means that the shape of the particle is changing while it is moving, while it is freely moving, and that is something which we are going to now prove, that what will happen with this analytical approach. So, as we have mentioned before, at t equals 0 I have to make a good gauge for the wave packet, and here I have considered a normalized stationary Gaussian wave packet. So, we are first looking at the stationary Gaussian wave packet where I do not use e to the power I k x part. This I remove. So, then the particle will be represented by this Gaussian function, which looks like this, is just a Gaussian function which is centered at x equals 0. There is no fast oscillation, because oscillation comes because of this e to the power I k x term. This term is missing, and that is why it is representing stationary Gaussian function. Why it is stationary Gaussian function? It is not it is stationary Gaussian function because of that missing part, that plane wave part here. And we have taken a normalized Gaussian function, that is also a requirement. We have to always begin with a normalized function in quantum dynamics. So, this is called normalized stationary Gaussian function, and then this is the final form of the Gaussian, final form of the wave packet. At different time I will be able to find out. So, if I know at t equals 0 time what I have, I will be able to find out at t equals any time, any later time, I will be able to find out what will be the typical shape of the wave function. So, for that I need to know a k, and we have seen that a k can be calculated from this. A k equals 2 pi minus infinity to plus infinity x 0 e to the power minus I k x dx, where this initial wave packet is given by this. So, I have to find out a k, then we have to plug that in here. I will be able to get the final form of the wave packet, analytical form of the wave packet, and I will be able to get the time evolution, how wave packet is evolving as a function of time, or in other words how the particle is evolving, its shape is changing, where it is going, every information will be able to get that. So, let us get this integration done first. So, if I plug that in here, it is going to be 1 by 2 pi, then 2a by pi to the power 1 by 4 then minus infinity to plus infinity integration e to the power minus a x square plus minus I kx then dx. And standard Gaussian integral, I have shown it before, and that's very useful. So we'll use this standard Gaussian integral here, and I get 1 by 2 pi 2a by pi to the power 1 by 4, and this integral gives me pi by a e to the power minus k square by 4a. So our task is to plug that in here, and in that case I will get 1 by 2 pi 2a by pi to the power 1 by 4 pi by a e to the power minus infinity to plus infinity e to the power minus k square by 4a e to the power minus e to the power I kx minus e t by h cut dk, where E is the kinetic energy given by h cut square k square by 2m. I will rearrange this one so that I can use the standard Gaussian integral. Minus infinity to plus infinity e to the power, I will rearrange in this following way, minus 1 by 4a plus I h cut t by 2m this k square plus I x k dk. Here I have inserted this E value. So this part is inserted, that's why I get this k square part, and this k square part is taken out, and I get I h cut t by 2m. So now I have got the standard integral, Gaussian integral, which can be now written as 2a by pi to the power 1 by 4 pi by a, and this integration is going to be pi by 1 by 4a plus I h cut t by 2m into e to the power minus x square divided by 4 1 by 4a plus I h cut t by 2m. So this part minus x square by 4 into 1 by 4a plus I h cut t by 2m, this can be written as ax square divided by 1 plus 2I h cut t a by m. We can write down this way. So, if we can write down, I will be able to write down this psi wave packet x t. I get the analytical form for that, and that is going to be, I just simplify the entire expression as 2a by pi to the power 1 by 4 square root of 1 by 1 plus 2I h cut t a by m e to the power minus a x square divided by 1 plus 2I h cut t a by m. That is the final expression for the wave packet, stationary wave packet at any time t. And finally, we are interested in density, because that can be connected to the experiment. So, we will get the density also, and for getting the density, what we will do, we in the previous here this part 2I not this part, we will assume that this 2 h cut t a by m equals b. So, this part can be represented in terms of b, this part also can be represented in terms of b, and that is the representation we have. If we represent it, then we get, this is the wave function where b equals this. No, this is density. So, we haven't reached there yet. So, first we have to represent in terms of b. So, we will represent it wave function, this wave function in terms of b, psi wave packet x t equals 2a by pi to the power 1 by 4 square root of 1 by 1 plus I b e to the power minus a x square divided by 1 plus I b. So, the density is going to be absolute value square equals 2a by pi to the power half square root of 1 by 1 plus I b into 1 minus I b, that is the complex conjugate, e to the power. So, this is nothing but psi star psi. So, we have to multiply by its complex conjugate. So, we can find out the complex conjugate form of this equation, of this expression, and then multiply with its own. So, e to the power, this is going to be e to the power minus a x square by 1 plus I b into e to the power minus a x square by 1 minus I b. This is the final wave packet form, and if I simplify this, I get 2a by pi to the power half square root of 1 by 1 plus b square e to the power minus 2a x square by 1 plus b square. So, we get this expression. So, what we have presented is that this is the density probability density distribution of that particle at t equals any time later time, and initial density distribution was this. So, these are the two different expressions we have for different time. This is the initial time and this was the final, this was the initial time and this was the final time, the density distribution. One thing is quite clear from here is that if I start with a Gaussian wave packet, a particle which is represented by a Gaussian wave packet, if I start with this a Gaussian wave packet, this was at t equals 0, this is Gaussian. We see that after even many times when the particle has propagated, it is still remaining to be Gaussian. There are some changes going on, we have to find out what kind of changes, but still this form e to the power minus something multiplied by x square form is still maintained. So, it is still a Gaussian function. So, good thing about this is that an initial stationary Gaussian free particle wave packet remains Gaussian when it is allowed to time evolve freely. It will maintain that the Gaussian form even after certain time. So, next what we will do, we will try to understand what are the changes we will expect for that Gaussian. For that we will find out the width of the Gaussian. So, I started with this which is centered at x equals 0 and the wave function, this was the density, maximum is 2a by pi to the power half, and initial width was delta x naught, that was the initial width. Let us say at t equals 0 we had an initial width of the Gaussian delta x naught, and delta x naught is defined as the delta x naught is the full width at half maximum of the Gaussian probability density profile. It is not the wave function, it is the probability density full width half max. We have to remember that. It is not the wave function full width half max, it is not that. It is the full width half max of the density profile. And if it is so, then I can find out this A value, because by definition it is going to be half full width at half maximum. So, half of its maximum value, that is 2a by pi 1 by half, it occurs when the function takes the value, this function takes the value when x equals delta x naught by 2. So, I get e to the power minus 2a delta x naught square by 4. Or I can get minus 2a delta x naught divided by 2 whole square equals ln 1 minus ln 2, or I can write down a equals 2 ln 2 by delta x naught square. I get the a value. Why I need this a value? Because I have to then plug that in here so that I can get the final expression for the later time. What is going on at the later time? For the later time, here I will do the same thing. This profile can be plotted. Let us say this profile is something like this, which is centered again x equals 0, and its width I will call it delta x t, because at time t its width, and I will compare with its width which I have got at, this is again psi x t density plot, and this is also psi x 0 density plot. This was delta x naught. So, I started with delta x naught. I will check what is going on with delta x t with after the time evolution for t time. So, by definition of full width half max, again half of its intensity, maximum intensity, this is the maximum intensity, half of its maximum intensity is obtained when the x is delta x t by 2, because this is delta x t by 2, this part is delta x t by 2. So, when xi, so I have to plug that in here, x value, which I get 2a by pi to the power 1 by half square root of 1 by 1 plus b square e to the power minus 2a. X is going to be delta x t square by 4 divided by 1 plus b square. So, what I have is now minus a delta x t whole square divided by two into 1 plus b square equals ln 1 minus ln 2, or delta x t whole square equals 2 into 1 plus b square ln 2 divided by a. A, we know a has certain value, we have already got this, a equals 2 ln 2 by delta t, sorry, delta x naught square. So, we can plug that in and we get finally 2 into 1 plus b square ln 2 delta x naught square divided by 2 ln 2, or delta x t whole square equals 1 plus b square delta x naught square. And we know that b we have already defined previously, b was 2 h cut T a by m. We know a, we can plug that in. So, finally, if we insert all these values, b value, then I get this expression delta x naught square. I am skipping few steps here. You can take a look at these steps very easily. It is tedious, but it is easy to do. 4 h cart square t square 2 ln 2 whole square divided by m square delta x naught square. Or on the other hand, I can have I can present it as delta x t is going to be now square root of delta x naught square plus 4 h cart square t square 2 ln 2 whole square divided by m square delta x naught square. Final expression for the with this delta x t at particular time t. So, what we observe from here is that delta x t is proportional to it will depend, it is not directly proportional, but it will depend on time. So, more time it spends during the evolution, it will just spread out more. It is just increasing delta t. It will increase the width of the stationary Gaussian. So, let us say I started with this Gaussian, slowly it will spread out, it will more spread out, and when it is spreading out, its amplitude will go down definitely, because total integration has to be 1. So, area under the curve has to be constant. So, its width is slowly increasing and the amplitude will go down. Amplitude going down can also be proved, because here the amplitude is given by its amplitude is given by this 2a by pi to the power half square root of 1 by 1 plus b square. This part is the amplitude of the wave packet at time t, and if I plug that in b, then I get an expression like this: a naught divided by there is an a naught here, we can write down 2a by pi to the power half. Now, I plug that in b, then I get square root of 1 plus 4 h cart square t square 2 ln 2 whole square divided by m square delta x naught square. What we see here is that amplitude will be inversely proportional with t and width is directly proportional with t. So, as we increase the t, amplitude will go down, just what we have presented here, amplitude will go down slowly and its width will slowly increase. So, that is the basic idea of stationary Gaussian wave packet motion. We will continue the session and we will see how this wave packet will behave if it is a travelling wave packet. So far we have said that the wave packet which is present is a stationary wave packet. So, the wave packet which is staying in a place, it is not changing, it is not changing the position, it is staying at the same position. But if it is staying here, as the time progresses, it will just spread out and its amplitude will go down. That is the behavior of a particle in quantum mechanics. We will meet again in the next session.